This paper explores approval-based committee voting under uncertainty, where voters express uncertain approval preferences over candidates. In contrast to existing work, which focuses on deterministic preferences, this study considers 4 different types of uncertain approval preference models: joint probability, lottery, candidate probability, and a restricted version of the latter. The authors initiate work on problems that take into account uncertain approval preferences to compute desirable committees that satisfy representation with high probability. They consider problems such as computing a committee with the highest probability of satisfying justified representation, Junior, a widely studied concept for fairness in approval-based committee voting. The authors undertake a detailed computational complexity analysis of several problems with respect to the 4 preference uncertainty models. They consider problems such as JR probability, is POS JR, is NEC JR, exists NEC JR, and max JR, with a central focus on justified representation. They also present results for stronger proportional representation axioms such as PJR and EJR. The study shows that exists NEC JR is NP complete for all the models considered, while is POS JR is computationally hard for the lottery model and polynomial time solvable for the other models. The results are summarized in Table 1. The authors note that their work combines aspects of uncertainty in preferences with approval-based committee voting, an area that has received significant interest in recent years. They cite existing work on winner determination with incomplete preferences, probability of a particular candidate winning an election under uncertain preferences, and facility location under uncertain information. The paper aims to provide a comprehensive analysis of uncertain approval preferences in approval-based committee voting, exploring the computational complexity of various problems and presenting results for different preference uncertainty models. The study contributes to the understanding of fairness and representation in collective decision-making under uncertainty. This research paper explores approval-based committee voting under uncertainty, focusing on various uncertain preference models and their computational complexity. The authors summarize their results in Table 1, which outlines the complexity of different problems related to justified representation, Junior, proportional justified representation, PJR, and extended justified representation, EJR, under uncertain preferences. The paper builds upon previous work by Imber et al. 15, and Halpern et al. 12, who examined approval-based committee voting under uncertainty and query complexity, respectively. The authors also draw inspiration from similar models in allocation and matching problems, as studied by Aziz et al. 1, 2, 5. In the deterministic approval-based committee, ABC, voting setting, a winning committee is said to satisfy Junior if every group of voters with a size greater than or equal to the committee size has at least one member with an approved candidate in the committee. PJR and EJR are strengthened notions of JR, where a committee satisfies PJR, EJR, if every cohesive group of voters has at least one, some, approved candidate in the committee. The authors introduce 3 uncertain preference models: the joint probability model, where voters have uncertain approval profiles with given probabilities; the lottery model, where each voter has a probability distribution over approval sets; and the candidate probability model, where each voter approves each candidate independently with a given probability. The paper's results highlight the computational complexity of problems such as checking whether a given committee is possibly or necessarily Junior, PJR, or EJR, as well as computing the committee that maximizes the probability of satisfying these axioms. The authors show that these problems are NP-complete or CONP-complete, depending on the uncertainty model and the specific problem considered. Here is the combined summary. In the context of approval-based committee voting under uncertainty, various models have been proposed to capture voters' preferences, including the 3-valued approval, 3VA, model, the joint probability model, and the lottery model. In the 3VA model, voters specify a subset of approved candidates, a subset of disapproved candidates, and the remaining candidates are considered uncertain with equal probability. The joint probability and lottery models have been studied in other contexts, while the 3VA model has been applied to ABC voting. A key concept in this work is the notion of plausible approval profiles, which can occur with positive probability under any of the uncertainty models. Proposition 1 establishes that there is a unique joint probability model representation for preferences given in the lottery model. Proposition 2 demonstrates that there is a unique lottery model representation for preferences given in the candidate probability model. The computational problems of interest include deciding whether a given committee satisfies the justified representation, junior, property with non-zero probability, is POS-JR, deciding whether there exists a committee that satisfies junior with non-zero probability, exists POS-JR, and computing the probability that a given committee satisfies JR probability. For the possible junior problem, exists POS-JR trivially has a yes answer for all probability models. Given a committee, is POS-JR can be solved in polynomial time for the joint probability, 3VA, and candidate probability models, but is NP complete for the lottery model, even when each voter assigns positive probability to at most 3 approval sets and k equals n, 2. The proof of Theorem 1 involves a reduction from 3 SAT, demonstrating that is POS-JR is NP complete for the lottery model. This result highlights the complexity of computing desirable committees under uncertainty, which is a crucial aspect of the proposed framework. Here is a combined summary of pages 7 and 8 of the research paper. The paper explores the concept of approval-based committee voting under uncertainty. It begins by proving that the problem of deciding whether a given committee W satisfies the justified representation, junior, criterion with probability 1 is solvable in polynomial time for the lottery model. This is achieved by defining a set V of voters who are not represented in W under at least one of their plausible approval sets and checking whether any candidate C in C, W is approved by at least K or more voters in V. If this condition is met, then W does not satisfy junior with probability 1. The paper then shifts focus to the necessary junior problem, which is deciding whether a given committee W satisfies junior with probability 1. This problem is shown to be solvable in polynomial time for the joint probability model, 3VA model, candidate probability model, and lottery model. Next, the paper explores the exists necessary junior problem, which is deciding whether there exists a committee W that satisfies junior with probability 1. This problem is shown to be NP complete for the 4 models by reducing from the NP complete problem of size JR. The size JR problem is to decide, given an instance, V, C, A, K, of ABC voting and a positive integer r less than k, whether there exists a committee W of size r that satisfies junior. The paper then presents 2 lemmas that provide further insights into the necessary junior problem. Lemma 1 shows that the size JR problem is NP complete by reducing from the NP complete problem of candidate cover. Lemma 2 shows that a committee W satisfies junior with probability 1 if and only if W equals C and K equals C, under the candidate probability model. Finally, the paper concludes that the exists necessary junior problem is NP complete for the candidate probability model by reducing from the NP complete problem of size JR. This result highlights the computational complexity of deciding whether a committee satisfies junior with probability 1 in the context of approval-based committee voting. The problem of deciding whether there exists a committee that satisfies the justified representation, junior, property with probability 1, denoted as exists nec JR, is shown to be NP complete for various voting models. Specifically, it is proven that exists nec JR is NP complete for the 3 VA models, lottery model, and joint probability model. The proof involves a reduction from the size JR problem, which is known to be NP complete. The reduction constructs a new instance I, from an instance I of size JR, where the number of voters and candidates is doubled, and the approval profiles are modified to ensure that the junior property is satisfied with probability 1. The reduction can be done in polynomial time, and it is shown that every yes instance of I is a yes instance of I, and vice versa. This implies that exists nec JR is NP complete for the aforementioned voting models. Furthermore, it is shown that exists nec JR remains NP complete even when minimal uncertainty is present, specifically when there are only 2 approval profiles associated with a positive probability. On the other hand, it is proven that exists nec JR is in P for the lottery model when each voter approves of only one candidate in each plausible approval profile. This result is obtained by counting the number of voters who potentially approve each candidate and selecting the candidates with a count greater than or equal to n(k). The results provide a comprehensive understanding of the computational complexity of the exists NEC-JR problem and highlight the challenges of finding committees that satisfy the junior property with probability 1 in various voting models. JR probability is the problem of determining the probability that a given committee W satisfies the joint responsibility, junior, property. Defined as P, W satisfies junior, equals underscore, element of A. Delta, A, times I, is JR, W, A, where I is an indicator function. The joint probability model takes approval profiles and their corresponding probability distributions as input. JR probability is in P for the joint probability model, but N-FARD for the lottery model. JR probability is P-complete for the 3VA model, which involves counting the number of plausible approval profiles for which W satisfies junior. To prove this, the authors reduce from vertex covers, the problem of counting the number of vertex covers for a given graph, which is P-complete. They show that every vertex cover in the graph corresponds to a unique plausible approval profile in the JR probability instance, and vice versa. The reduction involves creating a candidate for each edge in the graph and setting the approval probabilities accordingly. The authors also show that JR probability is in P for the 3VA model if the approval probabilities are binary, i.e., pi, C element of 0, 1. For all I in V and for all C in W. This is done by counting the number of plausible approval profiles that violate junior and using this count to compute the probability of W being junior. The computation involves counting the number of plausible assignments of vote as unknown approvals and using these counts to compute the probability of W violating junior. Additionally, the authors show that counting the plausible approval profiles where W satisfies junior can be computed in polynomial time if k equals n. This is done by ensuring that each voter who approves at least one candidate must have at least one of their approved candidates represented in the winning committee W. The objective is to count the number of plausible approval sets for each voter under which this condition is satisfied. The authors investigate the complexity of approval-based committee voting under uncertainty, specifically focusing on the justified representation, junior, and its stronger concepts, EJR and PJR. They introduce a novel formula to compute the count of plausible approval profiles, which can be computed in polynomial time. This leads to the discovery that max JR is N-FARD for all four uncertainty models considered. The authors then shift their attention to the stronger concepts of EJR and PJR, providing answers to the computational problems under these concepts. They prove that ISNEC EJR and ISNEC PJR, the problems of deciding whether a given committee satisfies EJR or PJR with probability 1, are both CONP complete for all four uncertainty models. Additionally, they show that exists NEC EJR and exists NEC PJR, the problems of deciding whether there exists a committee that satisfies EJR or PJR with probability 1, are CON-FARD for the candidate probability and 3VA models. The authors provide a proof for exists NEC EJR, reducing from as EJR, which is known to be CONP complete. They construct an instance I of exists NEC EJR from an instance I of as EJR, demonstrating that every yes instance of I is a yes instance of I, and vice versa. This reduction can be done in polynomial time. They also show that exists NEC EJR is CON-FARD for the lottery and joint probability models using similar arguments. Finally, the authors conclude that max EJR and max PJR, the problems of computing a committee with the highest probability of satisfying EJR or PJR, are CON-FARD for all four uncertainty models. This follows from the CONP hardness of exists NEC EJR and exists NEC PJR. The research paper formalizes uncertain preferences models for the well-studied committee selection problem, focusing on the concept of justified representation, junior. The central problem, max JR, is explored in four models: 3VA, candidate probability, lottery, and joint probability. The paper establishes that max EJR and max PJR are CON-FARD in these models, indicating the complexity of solving the justified representation problem under uncertainty. The authors suggest exploring other axiomatic properties, such as Pareto optimality, welfare maximization, or other notions of fairness, as potential future directions. Additionally, they note the importance of developing approximation or fixed parameter tractable (FPT) algorithms for the max-JR problem. The paper also mentions the possibility of exploring restricted versions of approval preferences. The authors acknowledge the support of various grants and funding schemes, including the NSF/CSIRO grant on fair sequential collective decision-making, and the ARC Laureate Project FL 200,100,204 on trustworthy AI. The paper provides a comprehensive list of references, highlighting the author's engagement with existing research in the field of computational social choice. Key concepts, such as justified representation, proportional representation, and uncertain preferences, are formally defined and analyzed. The paper employs technical terms and notation from the field of artificial intelligence and computer science, including complexity theory and algorithm design. The author's use of mathematical notation and equations, such as the definition of max-EJR and max-PJR, demonstrates the technical rigor of the research. The paper assumes a high level of familiarity with the subject matter, indicating that it is intended for an expert audience. The limitations of the research are acknowledged, with the authors noting the complexity of solving the justified representation problem under uncertainty. Future work directions are proposed, including the exploration of restricted domains and the development of approximation algorithms.